So we are going to move to liquids, which is a nice transition, because as we see at the beginning of this gas chapter, there is a temperature called critical temperature. Above the temperature, there is no clear distinction between liquid and gas. I mean, liquid and gas looks the same, so we cannot distinguish between them. What is the low temperature definition of a liquid? Usually people say if you put liquid inside the pot, the liquid will have the same shape like the pot and will not go out. For the gas, if you put gas inside the pot, the gas tries to occupy all possible space, right? But if you remember helium-2, the superfluid helium that is getting out of the pot and going everywhere, turns out that it's not always a good definition. So today we are going to speak about more scientific. What game was it last night? Today we are going to speak about more scientific definition of liquids based on the radial distribution function. And we are going to construct a radial distribution function for us. Okay, so we are going to see it in a moment. But let's start. And liquid B and I'm going to have 1 gram of liquid A and 2 gram of liquid B, and I'm going to mix them. Then I'm going to have A and B mixed, and total is going to be 2 grams. But now I'm asking about different problem. If I'm going to mix 1 liter with 1 liter, the question is, am I getting 2 liters? They will attract each other. Good. So if they attract each other, they will be smaller. If they repulse each other, it will be larger, right? Okay. So you can think this is never 2, but it is always around 2. Okay? This extra volume, extra, and you can say negative or positive volume has a name, and it's called excess volume. And this is a scientific paper from 1997, 10 years ago. But I mean, there are other papers more recent, but I just didn't find any. People are studying mixing of butanol with pentane, butanol with hexane, butanol with heptane, with octane, with trimethylpentane, and carbon tetrachloride at 2 different temperatures, 288 and 298. So what this paper is showing to you, that people really study these things. Even if we think that we know about liquids a lot, we don't know much. So people are still studying different reactions, just mixing. Nothing, no chemical, no chemistry at all. Just mixing of liquids. Well, but then you have the repulsion and attraction. You can say that there is a chemistry. We're going to see in a moment. Here is the excess volume for the mixture of butanol and pentane. Okay? And now you see that these numbers are very, very, very small. Here we have the amount of moles of butanol, and here we have the amount of moles of pentane. So when there is very, very little, 0.04% of the butanol, the excess volume is going to be positive. Very tiny positive number. Then it's becoming negative, negative, and negative. As you see, the largest negative one is probably around 284. It's a very, very small amount. We can make it on the plot. And here you have a mixture of the methanol with methyl nitrile. And you see that here the excess volume is always negative. Depend on the amount of one. In this case, you have only methanol. In this case, you have only CH3CN. So the largest volume lost is at this one. And you see that it's very small. This is over centimeters. Centimeters, cubic centimeters. So very small effect. Here you have another reaction of the ethanol with the same methyl nitrile. And you see that at the beginning, when there is a lot of ethanol, it's going to be positive. And then it's going to be negative. So the shape can be very strange. So in this case, when you are just adding some molecules of this inside ethanol, ethanol doesn't like it and is going to repulse it more, making empty spaces around each of these molecules, and that's why the volume goes larger. But later, when the number of these molecules is large, they start getting together, and you see finally it becomes negative, the excess volume. So it can be very strange shapes. Here you have the water with diaceton alcohol, two-dimensional, well, two, again, similar plots at different pressures. The black dots are at the pressure of 0.1 megapascal. This one is 60 megapascal, so very big difference in pressure. And you see that even liquid depends on the pressure a bit, not very much. This is a very small change from minus 1.4 to minus 1 centimeter, cubic centimeters for the excess volume. And it also happens when you are mixing three different things together. Here you have water, diaceton, and alcohol. 1, 2, 3. And you see that all of them has a minimum type of shape for the double crossing, for the double mixing. But also when you mix three of them, they are going to have minimum around here. So you see that in most of the cases, the excess volume is negative. And to understand how it happens, we have to study first radial distribution functions. And that you can understand better the radial distribution functions, first we are going to construct a radial distribution function. Okay. So again, radial distribution function. And now we are going to add what? What is the S for? S stands for students. So we have students' radial distribution function, and we are going to construct student radial distribution function. One 80 centimeters. This is 100 centimeters. Okay, keep this. I measure No, keep it as yourself, otherwise we don't have good results. 110. Okay, so now I'm getting 110. Where is the beginning? Maybe I need assistant for this. Come in, I will be my assistant. And Olesha will be second assistant writing the result on the blackboard. Come. So now we are measuring here. Keep on the top of her head that we get accurate results. 210. Okay, so for every student, we have just a volume like that. We are adding to the plot, okay? So just try to add. 210. This is 60, 120, 180, 240, 300, 360. Good. Next one. That would be 240, 280, 230, 210, and 260. Okay, can you sit on Nina's place? Yes. We need a substitute student. 170, and now on Olesha's place. 200. 200. Okay, we finish with one student. Now we go to the next one. 80, 120, oh sorry, 270, 220, 210, 120, 220, 130. Okay, choose the next student. Do you remember what was your distance to them? Okay. So we'll measure first, then go once again there. $120. 190. 150. 110. 100. 130. 210. 100. Thank you. 190. 280. Okay. I mean, as you see, we should go for all the students and measure 140, 200. 200. That would be 210. Ooh, maximal. 310. 220. 150. Oops. Should we measure the cameras too? This would be 100. 300 and 2 oleś. I know, but it's not enough, so just come closer a bit. Plus 60, 360. Okay, Nina, thank you very much. I think we are tired with constructing the radial distribution function. But anyway, the point is that I should go through all the students, and you already see what I'm getting, right? I'm getting the first peak here, and second peak here, then there is nothing, then there is something. Okay, and now this peak is for this separation. This peak is for this separation. Okay. This peak is for 1, 2 separation. 1, 2 separation. That's why we have maximum. Okay. This one will be for 3. 1, 2, 3. And also we get something like that. Or maybe 2. This one, in fact, may be a bit more complicated because can be a separation of 3 or can be separation 2 plus 2. 2 plus 2. Okay. Now, I'm saying it's a radial distribution function because it doesn't matter which direction. It's around me. But to be completely honest with you, if I do radial distribution function, then I'm getting another peak here. Well, maybe not so small, maybe big. Why? Because there is another classroom there. And there are students there, which is 4 meters difference. Okay? So, this plot is telling me at which distance I'm going to meet somebody. If this is a perfect crystal, it means if the students are sitting like that, then my plot is going to look like that. But the students are not sitting like that. All the table is a bit strange direction. So then I'm getting the peaks like that. Do you understand the idea of this? I think this is relatively simple. Now we can come back to our class. If we already know what is the radial distribution function. So, we have a molecule of liquid, and we have another molecules of liquid around. So what we are getting this violet area. And this violet area starts here, being that, then getting larger, 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 and always we count how many molecules is inside. This black area we count. Okay, you see this. In this case, they are counting something else. They are counting if the middle of the molecule is inside the violet or not. So in this case, the middle is inside, but in this case, it's just outside. So they count only 1, 2, 3. But we are going to make it nicer, smoother. So we are just always counting the area of the molecule that is inside the violet. And this plot is telling us what is the area. Here is 0 area. Okay? In fact, this one is also divided by the volume of this thing. you see that the volume of this thing is proportional. Well, I shouldn't say volume, I should say area. Area of this thing is proportional to 4 pi r1 square minus pi r2 square, where r1 is here and r2 is here. They are taking this difference very, very small, tiny. It doesn't matter for our case. So we can also say that this is A equal, I need some space. A equal 4, and for again the same, pi r plus dr square minus pi r square, which is going to be equal pi r square plus 2 pi r dr plus pi dr square minus pi r square. That is going to be equal, this cancels, 2 pi r dr plus pi dr square. But now dr is very small, so this one is approximately 0. So this is almost equal to 2 pi r dr. Good. So now radial distribution function is the amount of molecules inside the violet, so this part plus this part plus this part plus this part plus this part and so on, divided by this number, 2 pi r dr. Well, so it turns out that if I start from here, from the distance 0, there is 0 molecule inside, 0, 0, which kind of makes sense. Inside this molecule cannot be anything else. So it's 0, 0, 0, 0, 0, and then for some time again it's 0, because nothing wants to come very close. But then finally I'm starting having non-zero. And that's exactly this place, which is telling us where is the first neighbor. But you see that the first maximum, very sharp maximum, comes here, because that's the distance to the first neighbor. And there are 6 of them, making sharp peak. And then again, there is a place where they are not going to be neighbors, because it makes sense. If you go to this distance, there are not so many neighbors, because just this one were finished. And then the second neighbor starts. And you have the peak for the second neighbor. And then the peak for the third neighbor, and then it's going to be very, very smooth. So that's how we construct this radial distribution function for liquid. Exactly the same like for students. No big difference. Good. Let's see some real radial distribution functions. Well, we should start from ideal gas. Ideal gas has very strange radial distribution function. First, it goes to infinity here. Strange. Why? The point is that the ideal gas has 0 volume. I mean, one particle has 0 volume, it's a point. And the probability of finding other particles is exactly the same everywhere, because there is no interaction. If you have interaction, if you get very close, the energy goes up. But for ideal gas, no interaction. They can just travel without any interactions. So the same probability for finding the particle anywhere, but we are dividing by this, and we are dividing by r. And r is going to 0. So we are dividing by 0, so this one goes to infinity. Okay? This is for the ideal gas. But you see, nothing happens, nothing, not even one peak. It's boring. If you go to something real, that would be liquid argon. You see that it's exactly what we are showing on the previous plot. At some distance, there starts to be neighbors, and you see that this is around 3 angstrom. And then there is the first neighbor, second neighbor, and that's what we know about liquid argon. Let's go further. Now we have water, liquid water. This is taking a lot of people's activity to find these things. So what people do, they just take a water molecule, hydrogen, oxygen, hydrogen, oxygen, hydrogen, hydrogen. You see many molecules, put it inside the box, put temperature, and all the molecules are moving. And they let them move, and they just make a photo. Every 0.1 second they make a photo. And then from this photo, they are making these plots. This is the radial distribution function, distance between oxygen. So you have oxygen and oxygen and oxygen. They are measuring every distance between two oxygens and making a plot. You see that from this simulation you are getting very similar results. First neighbor, second neighbor, and after second neighbor I don't know what it is here. This is the oxygen hydrogen. And first peaks come extremely sharp. There is not enough scale to show it, because that's the distance between oxygen and hydrogen in a molecule, which is not changing. So it's very sharp, and every molecule has two such distances. So the first peak is very sharp. That's the chemically bound hydrogen. But later we have the next peak, and this is the hydrogen bond. Okay? So you have this hydrogen connects also to this oxygen. This oxygen connects to this hydrogen, and so on and so on. So that's the distance for the hydrogen bond. And later, you see that there is nothing here, really nothing, zero, which is unusual because there was always something, and almost nothing here. And then you have the next peak, and then it's going to be probably flat. Okay, let's go further. This is the experimental data for water. This is done with the X-ray scattering. And this is the distance between oxygen and oxygen. And different conditions. You see that these curves almost look the same. And again, what we see is that there is nothing, no oxygen come closer than 2 angstrom. There is one peak for the first neighbor, for the second neighbor, for the third neighbor, and over the third neighbor there is random distribution. You don't see anything more, no more order. The order goes, maybe there is a fourth neighbor, maybe very small. Let's go further. This is a comparison between solid and liquid. Okay. This is an interesting part, and this is going to be for water. So we have liquid water and we have ice. So what do you see? In the liquid water, let's take oxygen, oxygen again. First neighbor, second neighbor, third neighbor, and that's it. For ice, first neighbor, second. You see what's happening here. Many, many peaks. Because the ice is similar to the students in the class. It's sitting in the position, maybe sometimes off, maybe there are some problems in the crystal, but more or less the position to the next neighbor is well defined. So we have many, many, many peaks. But in water, when the situation is all the time changing, you have one molecule and around. When this is traveling, all around are traveling, but changing a bit. Turns out that this correlation between their traveling is visible only up to the fourth neighbor. Later you don't see anything. And you see it's not only for the oxygen-oxygen. It's also for the oxygen-hydrogen and hydrogen-hydrogen. There are many peaks. 1, 2, well, I don't know how to count this, but 3, 4, 5, 6, 7. But here you just see 1, 2, 3 peaks. Good. We should see how this one looks for gas. Still we have the example between liquid and solid. So this is sulfur, and this is solid sulfur. Liquid, solid, the same thing. You see that in liquid we have 1, 2, 3 peaks and then nothing. In solid, 1, 2, 3, 4, 5, 6, maybe 7. you see that the order is much better in solid. Here we have the comparison between solid, liquid, and gas for argon. So first, liquid is the black line and solid is the red line. Clearly there is a difference, big difference between solid and liquid. The solid is much better organized, but the liquid is much more diffused. What about the gas? Gas is the red curve. Gas has just the first neighbor and nothing more. So you see, when the gas is in 90 K, a low temperature, the first neighbor is very well defined. But when we go to high temperature, even the first neighbor is not so well defined, because the distance between two particles changing all the time. In this one, you can think that two particles of the gas kind of travel together always, because there is the first peak. And in liquid, the same temperature, notice, different pressure just. In liquid, you have already the peak structure. People are doing these things for more complicated systems. This is a mixture of water and methanol. So here you have the carbon-carbon. And carbon is only in methanol. There is no carbon in water. Okay? So, for example, when you have a mixture of water and methanol, you don't know when the water and water, or water, methanol, water, or methanol, 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 water, water, water. You don't know how it looks like. But these things from experiment give you the idea how far are methanol to methanol. And you see that one methanol to another methanol stays in the distance of 4 angstrom. What about the distance between methanol and water? Then we have to study OO, OH. Well, we would have to study CO, but we don't have here CO. So. But okay, water has oxygen and methanol has oxygen. So you can find the first oxygen here. This one can be between water and water, or maybe between water and methanol, or maybe methanol and methanol. If methanol and methanol, there should be another peak at 2 here, but there is no. So this is not methanol and methanol. But if you look at this more closer, it is exactly the same peak we observed for water before. Let's see, GOO, and let's go back a few pages. GOO is the blue one, but this is ice. Yeah. 1, 2, 3. Remember the blue curve. Now we come back. 1, 2, no 3. Second, this one is larger. So part of this comes from water-water, but part of this comes from water-methanol, which can give us the idea that water and methanol is at distance of 5 angstrom. And so on. By using these things, you can really find the internal structure of liquids. Aha. Here they divide it. This is between oxygen of water and oxygen of water. Oxygen of water, hydrogen of water. So you can separate these things. And finally, you can get a conclusion. Okay, radial distribution function doesn't tell you anything about the direction. But here we can get some idea from the direction. So if you have a water molecule being here with 2 hydrogens, one here and one here, you see that this is the water-water intermolecular spatial density. You see that the next water may come from this direction, may come from this direction, or may come anywhere from this direction, but not from here, not from here, not from here, which makes sense. Here is a hydrogen that can make hydrogen bond. Here is another hydrogen that can make a hydrogen bond. And here you have oxygen that can accept any hydrogen from there. This is for the first neighbor. This is for the second neighbor. So kind of interesting plots can be made out of this. You can make it not only for liquids, you can also check what happens for ions inside liquid. And this is also an interesting thing. If you take chlorine atom, well, chlorine ion, anion, you can ask the following question. How many molecules of water is around? One, or maybe two, or maybe three. This type of thing is called solvation layer. This is the first. Second solvation layer, third solvation layer, and so on and so on. So everybody can ask a question. If I have an anion, how many water molecules it attaches to itself? And how strong is this attachment? And exactly the radial distribution function is answering this question. Here, for example, you find that the hydrogen is much closer to the anion than the oxygen, which means that the water molecules always come with the hydrogen to the chlorine, with the other hydrogen pointing somewhere else. Okay, so this is the first thing. We know how it looks like. First, the hydrogen is very close, and later we have the oxygen farther. And the distance between these two is exactly the distance like between OH in water. But let's go farther. Hydrogen, then we have another hydrogen, but another hydrogen is this hydrogen distance. And again, a sharp peak. So maybe it's not very good to analyze hydrogens, it's better to do oxygen. So we have one peak for the first neighbor, second neighbor, and you see that's it. I mean, it would be nice to see farther, but you see that it's becoming noisy. So we believe that the solvation layers of chlorine anion are just two of them. The third one is already very loosely bound. Which is also interesting things, because if you have a solution of ions, cations, and when they are traveling, it's not just single ion traveling, it's a huge amount of water traveling together with the ion. Okay? Let's go further. No further. Good. So we discussed the difference between liquids, solids, and gases. Remember, gases, they have only first neighbor. And in high temperature, they don't even have the first neighbor. For liquids, they have the first neighbor, maybe the second neighbor, and maybe third one. But for solids, they have really many constant neighbors. And you can see this, the structure. And in my understanding, that's a real definition, the difference between solid, liquid, and gas. To look at the radial distribution function and count how many neighbors they are. If there is no structure, it's gas. If the structure is very, very, very rich, it's solid. But when the structure is between them, it's a liquid. But of course, you can remember the previous definitions that you studied of the liquid is taking the space taking the volume of the pot and making exactly the shape, like the shape of the pot, and gas expanding everywhere. But these are alternative descriptions of the same things, and I think they give you some more insight. Okay, thank you for today.